So where things left off last time was with having finished essentially the second pair of phase transitions in water and heading off to the third. Just to remind you what's up. So far I've talked about a first pair of phase transformations, which means converting one material phase, as in solid, into another one, like as in liquid. We've done the melting freezing transitions, so melting ice into water, freezing water into ice. Those occur at mostly as a function of temperature. If you're below 32 Fahrenheit, you get the freezing transition. Liquid water transforms into solid water. If you're above 32 Fahrenheit, solid water transforms into liquid water. And if you're right at 32, you can have the two existing in phase equilibrium. Neither one grows at the expense of the other. So why one specific temperature? Well, the rate at which liquid water molecules land on ice is pretty fixed by the density of the water. And the rate at which water molecules leave the ice for the water is fixed by the temperature. There's not much room to move, and there's really only one temperature at which you can get that landing and leaving rate imbalance. Any questions about melting freezing? Okay. Second pair of phase transformations was liquid water to gaseous water, as in steam. And back and forth, converting liquid water into gaseous water is evaporation. Converting gaseous water into liquid water is condensation. These are all just names for them. And those transformations involve more than just temperature. They involve also the density of the steam, which is flexible. You can change it. And as a result, you can get phase equilibrium. You can get the two phases to coexist in equilibrium, neither one growing at the expense of the other, over a broad range of temperatures. But you have to adjust the density of the gas right for that to happen. So at low temperature, when the leaving rate for water molecules from the solid water into the gas is slow, from the liquid water into gas is slow, you have to match that with a low landing rate. And how do you do that? Have a diffuse, not a very dense gas. So at lower temperatures, the liquid water and gaseous water can coexist, but you have to have a pretty fluffy, light steam. Not many water molecules per liter. At high temperatures, now the leaving rate for water molecules from the liquid into the gas is faster. They find the thermal energy they need to break free easier. And so you have to match that with a faster landing rate. So you need a denser steam to be in equilibrium. And we'll revisit those ideas when I talk about relative humidity, which is probably that part of that topic, the one that's most relevant to you. So I'll come back to that. All right. I talked about boiling. So to finish up, I talked about boiling. Boiling's nothing special in the sense that it's not a new phase transformation. It is simply liquid water becoming gaseous water, but with the added advantage that the water molecules that are landing and leaving can do this not just at the open surface of the liquid water, but within the liquid water. If there's a bubble there, a little void or empty spot, empty but for gas molecules in it, water can evaporate into the bubble. So suddenly you have a whole lot more surface available. If there are lots of bubbles inside liquid water, it's as though you spread the water out really thin and suddenly have lots of surface. And so the evaporation rate can become tremendously faster when water begins to boil. There is the issue of getting the bubble started in the first place, which was how we sort of finished up last time with the idea that they usually show up when you're heating water on the stove or in a kettle or something like that. But there are certain special cases where the bubbles fail to show up. And in that case, you don't actually get boiling not because it's not possible, but because there's no internal void in which the water molecules can evaporate. And just as sort of my public service announcement hat, in glass or glazed ceramic mugs and stuff like that, where there's basically the surface is so smooth right down to the molecular level, when you put water in such a surface in a container like that, You can heat it on with a microwave. It's about the only thing that'll do it. The microwave oven heats so uniformly. There are no hot spots. And so the bubbles don't start, and it is possible to superheat or overheat the water. It's hot enough to boil, but it doesn't boil because it can't create the first bubbles. And so you get water that's sort of dangerous. If you poke at it and create that first bubble, it boils violently. And to an extent, it explodes. All right. Any questions about the idea of boiling and why it happens? Again, to do public service announcement, aspects of boiling. Boiling occurs when the steam that is in phase equilibrium with the liquid water, when that steam is so dense that its pressure is atmospheric pressure. Why is this related to atmospheric pressure? Where'd that come from? It came from the fact that for a bubble of pure steam to survive in the middle of a container of water, it has to have a pressure that's at least as large as atmospheric pressure. If it's less than atmospheric pressure, it's going to be experiencing a pressure imbalance. The crush of atmospheric pressure is going to push inward on the skin of that bubble with a force that's greater than the steam inside will push out. And the skin of the bubble then will have a pressure imbalance across it, and it will accelerate towards the center of the bubble. And it will smush the steam out of existence. The steam will begin to condense and disappear. So a steam bubble that's not dense enough, and therefore doesn't have atmospheric pressure as its pressure or greater, it's going to be crushed out of existence by atmospheric pressure. All right? Well, atmospheric pressure down here near sea level, you can get steam with this local pressure at about 212 degrees Fahrenheit or 100 degrees Celsius. But if you go up in the mountains, way up high, I mean, the Blue Ridge is a starting point. Go into serious mountains, the atmospheric pressure is less for reasons we've talked about. As a result, you don't need as dense steam to be at atmospheric pressure, and it's easier for water to boil. It doesn't boil at the temperatures I mentioned earlier. It boils a little lower in temperature. And I guess by the time you get to Denver or something like that, and there's a song that has that as a line in it. Anyway, by the time you get to Denver, the pressure has dropped enough that water boils at, I think, gosh, I should know, 95 Celsius. It's a significant drop. Go up into the Rockies or go into the Himalayas. The water boils at a lower temperature, significantly lower. I think I figured at one point that on the top of Mount Everest, if you got water boiling, it would be too hot to keep your hand in for any length of time, but it wouldn't be all that hot. It wouldn't scald you the way it would putting your hand in boiling water down here will do. The point is, a demonstration I didn't do, is to boil water in vacuum. Water in a really low pressure, you can actually get water to boil at room temperature, which is just fun and games. So the water is, you can put your hand in it, it just feels at room temperature, but it is boiling because the steam bubbles that form just from room temperature water already are dense enough to stave off almost no pressure. It's okay. They don't get crushed. Well, why does it matter that the water boils at different temperatures at different altitudes? If you're cooking, it matters because a lot of cooking involves water evaporating, water boiling, in fact. Boiling an egg, for example, is the classic example. I told you earlier that when you put an egg in boiling water, what you're really doing is you're exposing that egg to a well-defined temperature, which down here near sea level is about 100 degrees Celsius. But if you go into the mountains, it's not 100 degrees Celsius anymore. Boiling water isn't that hot. It's maybe 95 Celsius, and the egg won't cook as fast, and you have to compensate. And this applies to all kinds of recipes. You're cooking a cake, it's different. And so if you are living at high altitude temporarily and or permanently, and you don't spend your life eating out, you may want to look at the recipes on some of the boxes for their high altitude cooking suggestions. Different temperatures, different times usually. And maybe if it's involving baking, it involves different temperatures of the oven, not of the food. Questions about the idea of why water boils at different temperatures at different altitudes? All right. That brings us then to the final pair of phase transformations, and that is the transformations from solid water to gaseous water. Skip the liquid. And you might think, well, that doesn't happen, but yes, it does, and you're familiar with it. It is quite possible for a solid to go directly into the gaseous phase, and for a gas to go directly into the solid phase. And if you have an ice cube just sitting out, and to look at it, and even if it's not, if it's cold, right out of the freezer, so that it's colder, it's so cold that it will not be in phase equilibrium at all with liquid water. No liquid water. There are still water molecules occasionally finding enough thermal energy there at the surface of the ice cube to leave. And when they do, that makes the ice cube smaller. If, on the other hand, water molecules in the air or just whatever space is above the ice cube manage to land on the ice cube and stick, they'll make the ice cube bigger. So that landing and leaving is taking place despite the fact that there's no liquid water around. You don't have to melt an ice cube to make it disappear as gas. And you've seen that if you've got frost-free freezers around, which most of the big freezers these days, not the dorm freezers, but the big freezers are so-called frost-free. I can talk later on about what it means to be frost-free, but they're basically the idea is the air inside them is almost devoid of water molecules, and as a result, you don't build up frost, which I'll talk about shortly. The point, though, is that when a water molecule leaves an ice cube in a frost-free freezer, it is usually not replaced because the landing rate's super slow. It's super dry air. And therefore, the water molecule leaves, it's gone, the ice cube's smaller. Water molecule leaves, it's gone, the ice cube's smaller still. And this explains why if you leave ice cubes around in a frost-free freezer and you come back a month later, they're like midget ice cubes. This has got to be familiar to most of you, right? They're just disappearing. And nobody left the freezer open to melt the ice. It's just getting smaller. Or the same effect occurs when it snows and stays cold for a long time, which is not like super common in Virginia, but it's common in other places. It snows, and then it just stays bitter cold for a week. And the snow, it snowed a little, and the snow just going away. Like you start to see the grass again. Like where did it go? Same effect. The water molecules left the ice and weren't replaced fast enough, and the ice just gets smaller. The snow being ice. That process is known as sublimation. Just giving it a name. Solids can sublime, and it sounds like some sort of paradise type thing, but it's not. Just sublimation is sublimation. Some number of materials are particularly prone to this sublimation. One of the most familiar ones is dry ice. If you've ever had dry ice around, you'll notice you never see liquid dry ice. It doesn't melt for complicated reasons. The liquid isn't around, but the solid just disappears. It leaves, it's solid carbon dioxide. It goes directly from the gas, from the solid to the gas, skips the liquid in just ordinary situations. So same with ice cubes. They just sublime. The gas molecules leave. In the era of incandescent light bulbs, which we're rapidly leaving, why does an incandescent light bulb fail? You know what I'm talking about with incandescent light bulb? The kind that had the filament in it, which is like, you guys still remember them, but boy, about 10 years from now, if I'm still doing this, I'll go like what? I mean, even these fluorescents are going to be dead as a dodo bird in about 10 years. It's going to be all LED lights. So teaching how things work is really a moving target. It's weird the number of things that have just vanished since I started doing this. Anyhow, so incandescent light bulbs. The reason incandescent light bulbs failed at all, in part why Edison was having so much trouble, he and others, Edison was not alone trying to invent the incandescent light bulb, is because at high temperatures that you need to get a good glow out of the good thermal radiation that you can see with your eyeballs, the temperature's so high, sublimation becomes really important. So carbon sublimes, tungsten sublimes, they all start losing atoms even though they don't melt. I mean, heating the filament to the point where it melts would be truly foolish, because then you'd lose the filament instantly. But even heating it hot near its melting temperature, it begins to lose atoms. Then you just head off by sublimation. Okay? Everybody okay with the idea of sublimation? And you've seen it in the freezer. Oh, so incidentally, this is freezer burn. So the foods that you put in the freezer without wrapping them properly, and you put them in a frost-free freezer, which has very dry air, they lose their moisture by sublimation, and then you come back and they're like astronaut food. They're all porous, dried out things, like what happened. And that is actually how they prepare certain foods to get the water out. They freeze dry them. Coffee was an example. People still drink freeze-dried coffee? Is that still popular? I don't know. I mean, it was a huge thing in my childhood. Wow, freeze-dried coffee. Basically, they're taking a container of coffee, they are cooling it to the point where it freezes, and then they just put it in super dry air and let the water molecules leave. And you end up with crystals of whatever's left that didn't evaporate. Didn't sublime. Okay? The opposite of sublimation, which occurs when the landing rate of water molecules on the ice is faster than the leaving rate of water molecules from the ice. The opposite possibility is called deposition. And deposition, it's used to make electronic devices all the time these days, is vapor deposition. The idea that you can take materials that are normally solid at room temperature, like all the stuff that makes up your electronic gadgets, some of that is applied to surfaces from the gas phase. It's a gas that then lands on a surface, and it lands faster than it leaves, and it accumulates. So this room is filled with gadgets that have been made in part with vapor deposition. But the more familiar case of deposition, or at least one that you encounter frequently, is called frost. If you have essentially moist air, that is air that has a lot of humidity in it, unlike the frost-free freezers where it's very dry, if you have moist air and a cold place, the landing rate will exceed the leaving rate, and you'll accumulate ice out of nothing. It'll come right out of the air. And frost is the familiar example of this, so that on a cold winter day, particularly if you've got poorly insulated windows, which I'll talk about in the next topic, it's cold outside, your room is humid, I don't know, for whatever reason, lots of reasons why the air inside your room might be hot and humid. When it encounters that cold window and comes near the cold window and its temperature drops, it suddenly, there's a lot of, it's a dense water vapor near a cold surface, and the landing rate is high because of the dense water vapor, and the leaving rate from the cold surface is low because it's cold. The water molecules can't get the energy to break free again, and they accumulate as frost. And hopefully you've all seen frost at some point or other and paid attention to it. It's often beautifully crystalline. As I said last time, it's a crystalline material whenever you've got the opportunity. And you can see facets and all sorts of things as you would in a quartz crystal, except that, okay, this is water, and one of the places where you see it best is in frost. It always shows up on your car windows and stuff if you get things out of balance between the temperature inside, the temperature outside, and the humidities. So you get frost on either the inside of the window or the outside of the window, and you see the crystal facets in that. Okay? Other example that you all are encountering, those of you who have dorm refrigerators, the cheap little boxes that they rent to you at about 89% of purchase price. In fact, it's probably worse. They probably make money renting it to you rather than selling it to you directly. You could throw it away and they'd be happy. Enough of that rant, though. Those refrigerators have a very cold box in them that you can put your 2 little ice cube trays or whatever they are in there. And over the course of the semester, that very cold box, we'll talk about how it managed to become so cold when I talk about how air conditioners work. It accumulates lots of frost. It just starts like just growing. Where did all this icy gunk come from? It came right out of the air by deposition. It's a very cold surface. Water molecules rarely leave it but they easily land on it, and then as they do, you accumulate more and more frost until eventually you have to defrost the thing or leave it for the person comes after you to deal with. Okay? Any questions about the phase transformation, solids to liquids and gases and all that? Okay. Last thing to talk about is relative humidity, which is worth talking about. Relative humidity is the measure of what fraction of the steam density you need to be in phase equilibrium with the other with the other relevant phase, which, say in this room, the other relevant phase for this room, there's not going to be, ice is not going to sit around in this room, it's going to melt. But liquid water could sit around, and liquid water and the gaseous water in the air, they're exchanging molecules all the time. And how close is the room air in this room to being in phase equilibrium with a pot of water all at the same temperature? If the humidity in this room, the relative humidity, were 100%, the water vapor in the air in this room and the liquid water in a pot would be in phase equilibrium. That's what 100% relative humidity means. That the steam is dense enough, the water vapor is dense enough in the air to be in phase equilibrium with the liquid water. The relative humidity is usually not 100%. It's usually less. In this room, it's probably, well, I'll guess it's 50%. And what that means is that there are only 50% as many water molecules per liter. The density is only 50% of what would be needed to be in phase equilibrium with liquid water. There's not, the steam is underdense, and therefore evaporation is going to be occurring. Not at 50% relative humidity, there are only 50% as many landings as you need to be in phase equilibrium. So the leavings are going to win. The water is going to evaporate. Not as fast as it would if the relative humidity were 0%, meaning there's no water molecules in the air, and there's no landing rate. But we're about 50% of the evaporation that takes place at half the rate it would if nothing were landing back on the liquid water. Do you see how those are related? The higher the relative humidity is, the more water molecules there are returning to the liquid water, and the harder it is for the liquid water to evaporate. Okay? You experience a net loss of water molecules into the gas. So relative humidity determines how fast things evaporate. If the relative humidity is 0, the evaporation is as fast as it can be at that temperature. Water molecules leave, none of them come back. If the relative humidity is 100%, then evaporation doesn't work at all, because the water molecules try to leave, but they're coming back as fast as they're leaving, and you make no net transfer. And at 50%, it's sort of halfway in between. Water molecules are leaving faster than they're returning, but it's not, it's somewhere in between the possibilities. You okay with the idea of a relative humidity? It works for liquids and air. It works for solids in air if you're down cold enough. In the environment of your dorm freezer thing, it's cold, and now the issue is between gaseous water and solid water. The importance then of relative humidity, and so where you're familiar with this, is in how it controls the evaporation and the condensation process. That is, the higher the relative humidity is, going from 0 working its way up to 100%, the harder it is for evaporation to work. And evaporation is familiar to us as a cooling mechanism. When our skins have water on them, when we sweat or glow, depending on your preference, water is, your body is putting water on its surface as a sort of a defense mechanism. It's trying to reduce, it's trying to get rid of heat. It's trying to convey heat out into the grand old world and not accumulate more than it can deal with. And so as you put liquid water on your skin, if the air is relatively dry, meaning the relative, or equivalent to saying that the relative humidity is low, the water molecules that appear on your skin will evaporate quickly. They will not be replaced. And so then there will be a net loss of water molecules very fast. And as they break free, there's an energy cost to that. they need the latent heat of evaporation to break free. So they have to gobble it up from their nearby environment, as in your body, and it's cooling to you. It removes heat from you. Heat from you flows into the water where it becomes a latent heat, where it pays the latent heat of evaporation needed to break the molecules, to separate the molecules and send them off as gas. So the faster that evaporation is taking place, the more cooling this effect is for you. If it's humid, as you well know, the evaporation doesn't cool you as well, and for good reason. When it's humid, that means there's a lot of return of water molecules back to liquid water, and so your skin, the sweat is sitting on your skin. It's trying to evaporate, but the water molecules are coming back almost as fast as they're leaving. Not many leave on average. You're still giving each water molecule that leaves its fraction, its proportion of latent heat of evaporation, but not many are leaving, so you're not losing very much thermal energy that way. And you feel uncomfortable. All right? Without this effect, the loss of heat by way of evaporation, we could not tolerate life in an environment that's body temperature hotter for sure, and even probably somewhat below body temperature. We need the ability to lose. We don't want heat flowing into us from a net flow of heat into us from high temperatures. If you're in a 110-degree desert or 120-degree desert, and you're just there without any strategies to deal with the temperature, you're going to be colder than the desert. Heat's going to flow into you. You're going to get hotter and hotter, and this is not good for you. So what do? You sweat, and you use this phase transition from liquid to gas to protect yourself from that high heat. If it's very humid in the desert, you're in trouble. And so there's sort of a balance between we can tolerate higher and higher temperatures as long as it gets drier and drier. High relative humidity and high temperature is really a problem for us. Any questions on that idea? Yeah. Okay. Anything else I want to say? Oh, just the last point, that there is what's known as the triple point for water, where water, steam, and ice, all three of them can be in phase equilibrium. Not surprisingly, it's very close to 32 Fahrenheit, because that's what's required to get water and ice to be in equilibrium. But you also can get, when you get steam at the right density as well, all three of them can coexist. And there's only one specific value at which it works for a given pressure. It's very, very close to 32 Fahrenheit, 0 Celsius. Any other questions about water, steam, and ice? Okay, that's good enough. I was going to talk about how salt melts water, melts ice, but that, can't do everything. This will go on to something else. Okay, so clothing, insulation, and climate. Yeah, I want to remember what I got. So I've talked about how heat flows from one thing to another because of a difference in their temperature. It flows by conduction, convection, radiation. And the bigger the temperature difference between two objects that are able to exchange heat, the more heat tends to flow, and it's complicated. The rules for governing that are details. What if you don't want the heat to flow? I've already alluded to that a little bit, talking about if you go into the desert where it's really hot, you don't really want heat flowing into you. You want to protect yourself against it. Similarly, if you go into a place where it's bitter cold, you don't want heat flowing out of you. You want to protect yourself against it. And so we have all these strategies, both sort of built into us and also into how we dress ourselves and protect ourselves for dealing with the flow of heat and trying to reduce it rather than encourage it. So suppose you were fighting a forest fire and you wanted to avoid being cooked. What would you wear? White, shiny black, flat metallic, silvery metallic. Flat black, silvery metallic. I can't even read. And actually I would say there are potentially two answers, but one of the, we'll come back to it. How many think white would be a good choice? Okay. How many think shiny black would be a good choice? How about flat black? How about silvery metallic? Okay, we're getting about a 50-50 on white and silvery metallic. And those are both potentially correct answers. The reason I'm waffling a little here, I couldn't ask this to you on an exam because white is problematic. We saw, or I told you before, that we see white with our eyes. And we say, you know, that's white. That is something that doesn't absorb light well and therefore doesn't emit thermal radiation in that range of visible light as well either. But I followed that up by saying that most things that appear white to our eyes, like all the white shirts in this room, it turns out in the infrared they're not white. They're black. They absorb and emit thermal radiation. They absorb infrared light very well, and they emit thermal radiation associated with room temperature and near room temperature very well. They're not actually white for real in the infrared. And finally I can remember to show you this as an example. We've got the little hot cube here. It's heated by a incandescent light bulb. If that ever burns out, we probably can't replace it. Anyhow, right now, this thermal radiation sensor, it's got a fancy name. It's called a bolometer, for whatever that's worth. It's looking at the shiny surface on this cube, and it doesn't see very much thermal radiation because the shiny surface is terrible at absorbing, in fact, any light, whether it's visible to our eyes or even in the infrared. It just bounces off. And so what the bolometer is seeing is its own temperature reflected back at it, its own thermal radiation reflected back at it. If I rotate the cube so that the black surface faces the bolometer, the reading goes way up. Because now the bolometer is not seeing its own thermal radiation reflected at it. The bolometer's thermal radiation going at the black is all absorbed, gone forever. But the black surface is doing as good a job as possible of emitting its own thermal radiation. It's hotter than the bolometer, therefore it's glowing more brightly than the bolometer, and the bolometer sees that extra strong glow. Which surface is which? This is a dull, shiny surface. That is, it's metallic, but it's been like sanded. So it's part of the way towards whiteness, but it's not white like white paint. It's white like ground metal. So it's still a metallic surface, and it's still pretty good at reflecting thermal radiation. So this guy will look pretty dark. As the bolometer is now seeing sort of its own reflection, but it's also seeing reflections from stuff off to the sides. Probably if I go over here, let's see. Can I be, how bright am I? Hi. Well, not really. Yeah. I guess I don't really glow. Okay. But where's the other surface? There. That surface is white as in white paint, or should be. Last I knew it was. And although it looks white to our eyes, in the infrared, which is what is relevant here, because the thermal radiation of the whole thermal radiation associated with this story, these devices, is in the infrared where you can't see it. This, if it were truly white in the infrared, would also emit relatively little light. The bolometer would see a diffuse reflection of itself in that white surface. But ta-da, it's not. The bolometer sees bright thermal radiation coming at it. Although that surface looks white, it's only white and visible. In the infrared, it's black. It's indistinguishable from the really black surface over here. There's, black, same thing, off scale. White over here, same thing, off scale. Black and white, can't tell them apart in the infrared. Any questions about, yeah? Is it possible to make a material that would show white on the infrared scale as well? Yes, ground metal. To an extent, ground metal will do it. That's what they're trying to do here. This surface here, which is ground metal, is doing its best to be, is trying to be white. There may actually be a few things that are genuinely white in the infrared. I can think how you would do it, but it's hard because so many things, all it takes is a tiny layer of an oxide on a metal to ruin its reflectivity. So for example, if they ground this metal a little more, and it had lots of little nooks and crannies, so that light coming in would bounce a couple times before going out, it can't tolerate those bounces because it's about 10% are getting absorbed every bounce. And so after a couple bounces, it's gone. So it probably is very hard to make something truly white in the infrared. Other questions? Okay. So I mean, just to answer this question, then, your best bet is not white clothing because you can't get real white in the infrared. Your best bet is silvery metallic, and in fact, the rescue equipment that forest fighters carry with them to self-rescue involves shiny metallic. All right, so clothing, it keeps you warm in cold places. It keeps you hot keeps you warm in cold places, cool in hot places. Same thing with insulation, basically. And the last piece is a seeming diversion, but trying to control the flow of heat is the activity of clothing and insulation. Climate also involves the control of flow, controlling the flow of heat. But in this case, it's from the earth to the sky, to the space beyond the earth, and we are mucking with that exchange of heat. We as people in society, and we've got to be careful with that. And that's where I'm heading. I don't think I'll get there today, but I'll give it a shot. Anyhow, okay. So how does clothing control thermal conduction, subsequently thermal convection, finally thermal radiation, and then finally about the Earth and climate? So we'll start off. How does clothing control thermal conduction? And so if a person is simply exposed, they're not wearing anything, they're just exposed to the hot environment or cold environment, they're going to begin exchanging heat with it. And how do you minimize that? Well, a first issue is don't touch solid materials, because solid materials tend to conduct heat better than gases. I mean, if you put things in a series of their ability to conduct heat, solid materials typically win over liquids, and solids and liquids certainly win over gases, just for conveying heat from one place to another. If you recall, thermal conduction depends on this bucket brigade behavior of the movement of heat by jostling atom after atom after atom after atom throughout the material, and potentially with the added effect of mobile electrons in conducting materials like metals. In a metal, the bucket brigade is there between atom after atom after atom, but it's dwarfed by the movement of heat by way of the electrons that whiz from one atom through a whole bunch of atoms to another atom and drop off heat and go back for more. So metals conduct heat well. Solids conduct heat significantly. Insulating solids conduct heat significantly less well, and gases are way down below that. So if you're trying to suppress heat flow, don't go touching metals. You don't want heat flowing into or out of your body. Don't touch metals. Particularly don't touch the good conducting metals like copper and aluminum. Stainless steel is a lot worse, so that might be a better choice. But you know from experience walking around, let's say, the bathroom in bare feet, that when you step on the nice, fluffy, shag, ruggy thing by the shower, okay, it doesn't feel much temperature at all. You don't hot, cold, don't really notice. But if you step, because you're touching an insulator that is kind of fluffy. We'll talk about that too. You're actually not touching very much. You're touching a lot of air. When you take your foot off and you step on the tile, the ceramic tile, feels considerably cooler usually. It's at the same, those two things are at the same temperature, but the tile is a better conductor of heat than that fluffy carpet. And as a result, heat flows out of you into the tile and through the tile much faster than it flows out of you and into the carpet and through the carpet and away from you. It kind of accumulates right near your skin on the carpet. And you quickly bring the carpet up to the same temperature as your foot, and that's pretty much the end for heat transfer, and you don't feel any more cooling effect. Tile, you keep losing heat to the tile because it keeps wicking the heat out to more and more of the tile by way of thermal conduction. And if you step on a piece of metal, a plate of copper, it feels very cold. Why? Because your heat from your foot flows by conduction into the copper and then wicks through the copper by way of its wonderful thermal conductivity all the way out into the suburbs. And you feel that loss of heat dramatically. It's much colder. So hopefully this is familiar to you. When you touch stuff that's cold, but all at the same temperature, the ceramics, glass stuff, it feels it's cool. But the metals, ooh, much worse. The heat's flowing out of you much faster because it's going all along the metal quickly. When your friends encourage you to touch your tongue on a bitter cold day to stuff, touching the wood was okay. Touching the metal, not so much. Because it sucks so much heat out, it freezes your tongue on, and then you're calling 911. Okay. Yeah, at least you got a phone. Back in my day, we had to walk 5 miles through the snow. All right, anyhow. Okay, so that's conduction. Trying to control conduction, you want insulation and clothing. You try to use materials that have as small thermal conductivities as possible. Now, just actually to look at this equation, the flow of heat from one surface to another depends fairly simply on a couple things. The conductivity of the material. I will not ever test you on this equation. This is like worth seeing once, having, that's it. Okay, the conductivity matters. The bigger the conductivity is, the more heat flows for a given situation. So copper has a huge thermal conductivity. Glass, for example, has a very poor thermal conductivity. The temperature difference matters. So if you're going from one side of a plate to another side of a plate, and the difference is 1 degree, well, you get some heat flow. If it's 10 degrees, you'll probably get 10 times the heat flow. It's a bigger gradient in temperature as a result. And the flow of heat through conductivity goes up approximately in proportion to the thermal gradient. Area matters because the bigger the plate is that you're flowing through, the more heat flows. For each portion of plate, each square foot of plate carries its own dose of heat. So if you've got 1 square foot, you get 1 dose of heat flowing through it. You got 10 square feet of plate, you got 10 doses of heat flowing through it. So it shouldn't come as any surprise that area matters. And thickness finally matters too, but 1 over thickness. The closer the hot and cold are to each other, the more ferocious the gradient of temperature is, and the faster the heat flows through things. So a thin piece of glass carries heat much better than a thick piece of glass. And so the same would be true of stone. So if you're Hamlet or Ophelia or whatever, and you wanted to stay warm on a cold Danish night, you wanted a very thick stone. The thicker, the more gradual the temperature gradient, and the more likely you were to stay decently warm. But stone, it turns out, isn't a good enough. It conducts heat too well, and so castles are notoriously cold in the winter. We can do better. Stone, solid materials are not the best at blocking heat flow. We don't wear stone clothing either. So what do we use to limit thermal conductivity in the way of clothing, and actually in most insulation as well? And so I'll ask you a question here with this. Suppose you have 2 wool sweaters, and they are both 1 centimeter thick. So they're indistinguishable from one another, except one of the sweaters weighs 50% more than the other. It's just heavier. It's got more wool packed in more tightly. Can you picture those 2 sweaters? Nothing different about them except one's got more sheep's wool. Which sweater provides you with the best insulation of those two? How many think it's the heavier sweater that's the better insulator? How many think it's the lighter sweater that's the better insulator? Okay, the vast majority are going for heavier insulator. And I'll tell you it's not. It's actually the lighter sweater. You want, because what's the what do you think is the actual insulator in a sweater? The wool or something else? What else is in the sweater? Air. Air, it turns out, is the better insulator than wool by a huge margin. And so the wool's job is not to be the insulator. It is to keep the air from moving and to prevent convection. So what the main purpose of clothing is to keep it uses air as the insulator, which is because air is a terrible conductor of heat in comparison to any of the solids. It's a way better insulator than any solid you can choose. But however, air can move. And if it moves, if it undergoes convection or if it's blown off or any of that sort of thing, then you can start losing heat or gaining heat depending on whether you're in a cold environment or a hot environment. So you need clothing to keep the air in place, to trap it. And that's true not only of clothing, but most insulations in your house are these fine fibrous things. Most clothing naturally is fine fiber. We have hair. You know, why do we have hair rather than a helmet of, I don't know, whatever, like rhinoceros stuff, which I guess is hair too. But anyhow, it's because hair is a much better insulator, not because of the hair, but because the air the hair traps. Boy, is that messy to say. So it doesn't take a lot of hair to hold the air in place. And we know what is involved. It's the drag forces. Finely divided stuff traps the air by if the air tries to flow past, it's experiencing viscous drag and potentially pressure drag depending on what the situation is. And so finely divided fabrics, fibers, are there for trapping the air. Household insulation, if I get around to doing some of these things. Household insulation, the classic modern, reasonably modern household insulation is fiberglass. I guess there are issues about whether fiberglass is sort of human safe. The little fibers are not great to get in your body, but as he holds it. But the main insulation in fiberglass is not the glass. It's the air trapped by the glass. And so when you put this on your walls, and particularly when you're insulating your house, one of the most important things to insulate is the attic and the roof, because the heat if you've got a hot box, where are you going to lose the heat? You're going to heat the air at the top, and up it goes, right? Buoyant. It's naturally buoyant. So houses lose a lot of heat through their roofs if they're not careful. And so you put fiberglass there to prevent convection from lifting heat off the ceiling. It's got to work. The heat's got to work its way through all these fibers and the little packages of air. Another familiar insulation that uses the same effect is styrofoam and all of the related foams. You know, how is it you can hold a nearly boiling hot coffee or tea in a cup that's only 1/8 of an inch thick or less? It's really thin. It's because it's not the polystyrene plastic. If you took a dense plastic cup, conventional plastic cup, you would burn your hand. You know this. There's no styrofoam cups left, so they give you one of the red cups that's dump the beer out and then put in coffee. It burns your hand. It's not a good enough insulator. The plastic itself, not so good. But the tiny gas bubbles are very good insulators. So a lot of houses now also have styrofoam as the insulator, or related foams. So the heat's got to work its way through all these gas pockets, and it does a terrible job. All right, I'll continue with insulation and climate on Wednesday.